Recording is rolling. So here's our agenda. Oh, you guys remember check focus, make sure you got all your assignments in. I'm still waiting for a couple of quizzes from students here and there. I do want to get you guys' quizzes back to you so you can see how you did. I want to post the solutions. You guys can do corrections for partial points, all that stuff. Right. For now, yeah, let's get back to this puzzle cup you guys have been thinking about this week. So recap how the story works. You guys remember that if you fill this cup up halfway with water, it holds the water perfectly fine. You guys remember, got straw hole here from this point of view. Turn it upside down. You guys see a straw hole, right? So fill it up halfway with water. Water stays in the cup. If you fill it to the brim with water, the water starts draining out the bottom, and it doesn't stop draining until the entire cup is drained. Right? The water level doesn't just go back to the previous level where it was perfectly happy before. No, the entire cup drains. So who's figured it out? Who wants to tell me how? What's going on with the straw inside the cup? Yeah, what do you think?
Does it have something to do with static friction?
No. Look for something else. Okay, so what's going on with the straw? Not a friction thing. It's a.
Is it capillary action?
That might possibly be related. True. Yeah, I don't think that's exactly what I'm looking for though.
Thermal force?
What's that?
Thermal force?
No, yeah, different kind of thing going on, right? In fact, maybe I should give you guys a hint. It's actually actually this is related to something I haven't explicitly gone over in this class. Right? I haven't told you guys about pressure yet, so we throw that. Pressure. Do you guys want to know what the definition of pressure is? Force per unit area. Force per unit area. Right? You can also rearrange this. You can say a force is a pressure multiplied by an area, right? Maybe like a pressure difference times area could result in a force, something like that. Right? And this will have units, right? Like you guys know, force is measured in newtons. You guys know area is measured in square meters. So couldn't pressure be measured in newtons per square meter? Right? And actually, newtons per square meter has its own name. Does anybody happen to know what it's called? Called a Pascal. It's written as PA. So that stands for, that's a unit Pascal, where 1 Pascal is the same thing as 1 Newton per square meter. Now that's metric units, which we're doing in this class. But you know what? I bet you guys actually are familiar with pressure from American units. Well, I should say imperial units, whatever. We use them in the States. You guys pump up your bike tires? You guys buy a pump from an American store, got an American pump, and what unit does it say on the pump? PSI. PSI. Okay. So same idea. Now, really, this is a ratio, right? What does PSI stand for? Yeah, pounds per square inch. So it's really this. It's pounds per square inch. This is a better way to think of it. That's really what it is, right? Hey, isn't that the same idea? Look, pounds per square inch, newtons per square meter. That's some kind of force per unit area, isn't it? Is that? Okay. Now, does anybody happen to know, are we in a pressure right now? We are. It's actually an enormous pressure. Does anybody happen to know what 1 atmosphere of pressure is equivalent to, either in terms of pascals or PSI? Okay. I guess if you don't know, then no is the right answer. So I'll tell you in metric units first. Right? So newtons per square meter. Well, newtons per square meter. Think about it like this. You guys know that 100 grams. This is 100 grams right here. This weighs very close to 1 Newton. It's like 0.98 newtons, basically 1 Newton, right? And if you look at the tiles on the floor, if you count 3 by 3, that could be like 9 tiles. Isn't that really close to a square meter? Right, really close to. Okay. So if you put this on say a board that was like 1 square meter, it's about 9 tiles, like 3 by 3. Okay. That'd be approximately representative of 1 Pascal. Now, I wonder how much atmospheric pressure there is that's pushing on us right now. How many of those there are? Well, it's actually 101,000 pascals. Yeah, pretty crazy, isn't it? Right? Do you guys know what that is in PSI? 14.7.
It's close.
Now, context for that, guys. How much does a bowling ball weigh? A bowling ball?
A lot.
Yeah, probably about 10 or 15 pounds, right? Hey, if you took a bowling ball and put it on every single square inch of your skin, whoa, that's actually what's going on right now. Right? You guys actually have that much pressure on you right now. I mean, you would definitely notice it if it was gone, right? Right. So if you you're like, I'm in the vacuum, where will pressure go? It just feels like normal to us right now, but that's actually a quantity of this pressure, and that is related to this puzzle cup. And I'll come back later on and tell you guys why. This just has something to do with pressure. If this cup were in a vacuum, this actually would not work. Okay? Any last guesses before I give you the answer? Any last guesses? What's going on with the straw? Yeah, Brock. Okay, possibly related to that. But what is the straw doing? Like, say if you wanted to go home and construct one of these yourself, like, I can't wait to make my own griffin cup. How'd you do that? Take the straw. Got it up the side.
Oh.
I've seen that before.
Yeah, what does that have to do with atmospheric pressure? Well, I'll take you guys back through the story. Tell you why. So you guys remember the first thing you did was fill it halfway with water. So, well, let's pretend that's half. Right, so if you fill it partway with water, yeah, part of the water will go into the straw, but only up to about that point. The water is contained within the cup. Okay, so it's all good. Could function as a normal cup. It's all good. Okay. But suppose you were particularly greedy, and this cup goes by a name. I want even more water. Give me all the water. This is called a greedy cup, or maybe the more maybe a better Pythagoras cup. Maybe a more dignified name, Pythagoras cup. Yeah, this cup goes back thousands of years ago. Hey, that's the triangle guy. Yeah. Yeah. He did some other things too. He made all his guess what. So his greedy guess anyway.
He made a cup.
So yeah, you fill this up to the brim with water, right? And now the straw becomes flooded, doesn't it? So water starts flowing out the bottom. Just like things roll downhill, water flows downhill. The lowest point would be the bottom of the cup, so it starts to drain out. Okay. Now, there's a last twist to the story, though, which is when the water level goes back to the original level. Well, now there's been a state change because the water's still flooding the straw, isn't it? Okay. And the rest of it gets siphoned out. Now, here's where the atmospheric pressure kicks in and becomes important. Because why would this not work in a vacuum? But besides the fact that water actually would boil away in the vacuum, that's kind of a side deal. There are two things that cause boiling. One is an increase in temperature. The other is a decrease in pressure. You can sort of show that with this. This isn't water. This is ethanol. But so if you heat it up a little bit, let's say with your body temperature, and there's like a low pressure in here, then that's enough to cause a state change. That aside, though, suppose there's some liquid that could exist in the vacuum. Why would this still not work? Because when the water level gets back to the original level down here, and the straw is flooded, what it would do is it would just split. And then half of it would fall to the left, half of it would fall to the right, and then the water level would actually stop, and the whole cup would not drain. It would just stay halfway. Right? But that can't happen if you have, say, like 14.7 pounds per square inch or 100,000 pascals, like all pushing everywhere. This water, it can't split here. It can't just create a vacuum because it's all being pushed together as one continuous mass, and so the entire water gets siphoned out. Okay? Which actually sets up the next question of, I wonder, suppose you wanted to build one of these on the side of the road, maybe some kind of like highway trash line. We built the world's largest Pythagoras cup off the side of I-95. I wonder if there's like some maximum size you could build this cup. Like what is I'll call it H max. What's the largest you could, because Earth's pressure, even though it's enormously huge, it is finite, isn't it? Right? So I wonder how high you could build this before, say, the pressure isn't enough to actually hold this together. Say, where it actually does go to a vacuum and it actually would split. Does anybody have a pretty good guess how high you could build this cup? Okay, let me turn that question around. Let's say you're standing on the side of a pool, and then maybe you and your friends are down by the deep end. You're looking over, like, hey, let's dive in the deep end. I don't know, that looks real scary. And then, okay, so it's like deep end of the pool, it's all down there. Okay, so you're looking out at the deep end, and then you dive down to the water. You start going down. I guess that's filled with water. Like, it'd be a bad thing. I forgot you put it in the water. So can you guys feel as you're diving down into the water? Feel the pressure going up, 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 up. You guys can feel it, right? How deep would you have to go to effectively reach another atmosphere of pressure? Like we're at 1 atmosphere here at the surface. How deep would you have to go to get to 2 atmospheres of pressure? Who said 10 meters? Winner! It's about 10.3 meters. No, this is, yeah, so if you dive down 10.3 meters of water, that would also match Earth's atmospheric pressure. It's about, what, 30-something feet, something like that? That's also the answer to this question with the Pythagoras cup. Because if you tried to pump water up, suppose you had, you guys know if I dunk this upside down water and draw it up this way, I can start draw some of the water up in the cup. You can only do that up to 10.3 meters. They had a big like glass vial. This is the way the first barometers were designed too. Well, they used mercury because that's way more dense than water, but you could, in theory, do this with water too. You can only pump it up to an H max of 10.3 meters. So this would be 10.3 meters. The history story behind this, people first discovered this, as far as I know, when pumps were invented. So the story goes, there would be these towns, say at the top of a hill. There's a little town up here. This one's a church. And then say there's a lake at the bottom, and we need some fresh water down from this lake. Okay. So we got to walk down and fill pedal with water and walk back up, and that's taking forever. And then finally, one day pumps were invented. We're like, hey, we could just throw a pipe down here, and we could just like pump the water up, pump up. And then a bunch of towns started to do this. They all started to copy this idea. Like, oh man, this is way easier. We don't have to climb these stairs all day with pails of water. But then some towns would notice if they were on really tall hills that there actually was a maximum that they could pump it up to. And guess what that maximum is? 10.3 meters. 10.3 meters. Okay. And because at 10.3 meters, see the pressure would actually become less and less and less the farther up you go, and it actually becomes 0 atmospheres, 0 pascals, 0 psi right here, and the water actually starts boiling. Yeah, so that's much you can go up. Right. Let's get some back. All right, so where are we on our agenda? Okay. So see, whatever that Pythagoras cup. Okay. I've got an FRQ lineup for you guys.